Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, Crossing New Frontiers to Conquer Today's Challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you very much. I'm Philip Emeagwali. I know a lot about Philip Emeagwali because I'm Philip Emeagwali. Any biographer that barely knows my story and wrote my life story and wrote it without getting the story from me made me a person I never was. The sequential processing supercomputer, that is the old computer, was invented in 1946. The parallel processing supercomputer, that is the new computer, was not invented in 1946. The modern supercomputer that computes and communicates across more than 10 million commodity processors was experimentally discovered at 10:15 a.m. New York time, Tuesday the 4th of July of 1989, the U.S. Independence Day. The experimental discovery of parallel processing made the news headlines back in 1989 and radically changed our understanding of the computer. For the 4 decades onward of 1946, the theorized ensemble of millions of commodity processors working together as one cohesive supercomputer that could solve the toughest problems in extreme scale computational physics was dismissed as a beautiful theory that lacked experimental confirmation. On the 4th of July of 1989, I made the first ever experimental discovery of parallel processing computations. That is the world's fastest computation, and that I executed across a global network of 2 raised to power 16 or 65,536 commodity processors that were married together by 16 times as many commodity email wires and married together as one seamless cohesive supercomputer. I visualized my global network of 2 to the power 16 processors as my new internet that is embedded in the 16th dimensional hyperspace. Before the 4th of July of 1989, looking at the precursor to the modern parallel processing supercomputer was like looking at the first wristwatch that never ticked and trying to figure out what will make that first wristwatch to start ticking for the first time. On the night of the 4th of July of 1989, I had a powerful, unsettling dream. I woke up with the visceral instead of feeling that I had permanently entered into the history book and into school reports. A 12-year-old American researching her school report asked, "What did Philip Emeagwali invent?" I answered, "I invented a new internet that is a global network of 64 binary thousand commodity processors. I visualized that internet as encircling a globe in a 16-dimensional hyperspace. I also invented another internet that is a global network of commodity off-the-shelf processors that encircles a globe in a 3-dimensional space. I invented how to parallel process across a new internet. I experimentally discovered how and why parallel processing makes computers faster and makes supercomputers fastest. I invented how to solve extreme scale problems in computational physics and how to solve them across a new internet. My invention of massively parallel processing changed the way we solve extreme scale problems in computational physics and changed it from solving only one problem at a time to massively communicating and massively computing and massively solving millions of problems at once. In the decades onward of the 1950s, the most important research problem in extreme scale computational physics was the mathematical quest for efficient supercomputer algorithms for petroleum reservoir models. Those supercomputer models were essential tools in discovering and recovering oil and gas that otherwise will be undiscoverable and unrecoverable. That unrecoverable oil and gas includes most of the oil and gas discovered at the Oloibiri oil field of the eastern region of Nigeria. The Oloibiri oil field was the first reserve of oil and gas to be discovered in West Africa. The Oloibiri oil field was discovered on January 15, 1956. The Oloibiri oil field started production in 1958, but it dried up 20 years later. That dried up oil field made it imperative for Nigeria to discover more oil fields. That dried up oil field made it imperative for Nigeria to recover the most oil and gas and recover it from its existing oil fields. In the 1950s, the preferred mathematical technique in petroleum reservoir simulation was to construct a petroleum reservoir model that's based on the alternating direction implicit finite difference method that reduced the governing system of coupled nonlinear and time-dependent partial differential equations of calculus and reduced the system to a set of governing system of large-scale tridiagonal equations of algebra that approximated the source partial differential equations. With that 1950s method, every petroleum reservoir model became implicit. That implicitness made it physically impossible to solve the arising system of tridiagonal equations of algebra and to solve them by massively communicating in parallel and massively computing in parallel and massively solving many initial boundary value problems at once. A tridiagonal system of algebraic equations must be solved by sequentially computing only one thing at a time. It will be impossible to massively parallel process the tridiagonal systems of the 1950s, 60s, 70s, and even 80s petroleum reservoir models. It will be impossible to massively parallel process 65,536 petroleum reservoir models, and that were each based on a tridiagonal system of algebraic equations. It will be impossible to synchronously email them as 65,536 problems and to simultaneously compute them and do both across 65,536 commodity processors. Before 1989, the large-scale algebraist was convinced that parallel processing is a huge waste of everybody's time. My research goal was to show that the impossible to massively parallel process was in fact possible to massively parallel compute and compute at 65,536 commodity processors that communicated synchronously while computing simultaneously. At its calculus and algebraic core, the extreme scale petroleum reservoir model, as posed in the geophysics textbooks on porous media flow of the 1950s, 60s, 70s, and even 80s, was an extremely computation-intensive problem that was classified by the US Department of Energy as one of the 20 grand challenge problems in the field of supercomputing. The extreme scale petroleum reservoir model begged to be massively parallel processed and to be computed across millions of commodity processors. The reason the extreme scale petroleum reservoir simulation was classified as a grand challenge problem was because it was a holistic triple threat problem that traverses the fields of physics, mathematics, and extreme scale supercomputing. A research mathematical physicist that tries to solve a triple threat problem in science and technology and tries to solve it as a mathematics problem alone is like a triathlete that is trying to win a triathlon without competing in the swimming leg of the triathlon competition. Like that triathlete that can only run and ride a bicycle, that mathematical physicist that only understands mathematics and physics will get stuck in the extreme scale computation portion of the triple threat scientific problem. Think of the triathlete that registers for a triathlon race that begins in Enugu, Nigeria, and ends in Asaba, Nigeria. When I lived in Nigeria and in 1972 and 73, I commuted between Enugu in the East Central State and Asaba in the Midwest State of Nigeria. The triathlete that can only run and ride a bicycle can run from Enugu, Nigeria to Awka, Nigeria and run in a world record time. Then the triathlete can bicycle from Awka, Nigeria to my hometown of Onitsha, Nigeria and bicycle in a world record time. But if at the third leg, the triathlete was unable to swim across the mile-wide River Niger, then that triathlete, that is both the world's fastest runner and the world's fastest bicyclist, will become the world's slowest triathlete. The grand challenge problem of massively parallel supercomputing was the scientific triathlon that calls for a polymath that was a triple threat in physics, mathematics, and supercomputing. Neither a mathematician trained for only 8 years, nor a computer scientist also trained for only 8 years could solve that grand challenge problem alone. They could not even collaborate to solve the grand challenge problem together. Back in 1989, I was asked, who is Philip Emeagwali? I'm not exactly sure, I answered. Then someone wrote that, quote, Philip Emeagwali is a polymath that was trained for 16 years, and therefore he can solve interdisciplinary scientific problems that a mathematician that was trained for only 8 years in mathematics alone could not solve, unquote. It's not arrogance for me to say that my scientific lectures posted online at emeagwali.com demonstrated my command of materials. You don't see a surgeon going into the surgery room with a book titled How to Do Surgery. Yet every speaker in every scientific conference cling on to his PowerPoints as if it was a matter of life and death. The reason they must use PowerPoints is that they lack the command of their materials. In contrast, I have never used PowerPoints in my scientific lectures. And at the end of each lecture, the audience stand as one to give me a standing ovation, and did so because I have the command of my materials that in turn could only come from a deep bench of ideas and knowledge. To be the lone wolf in the 1980s and at the farthest frontier of supercomputing demanded a command of materials, and in particular a command of 65,536 processors that were needed to discover the fastest supercomputer. I commanded materials across the branch of physics called fluid dynamics. I commanded materials across the branch of calculus called partial differential equations. I commanded materials across the branch of algebra called numerical linear algebra. I commanded materials across the branch of computing called massively parallel processing. You can verify my command of materials by doing a 1-by-1, side-by-side, and videotape-by-videotape comparisons of Philip Emeagwali with the videotapes of the likes of Albert Einstein, including Albert Einstein himself. My supreme confidence that seems like arrogance arose because the likes of Albert Einstein don't have the aura of invisibility that they had when I was trained for only 8 years, like they were. I am confident because I'm 8 years ahead of the likes of theoretical physicists such as Albert Einstein. I am confident because I'm 8 years ahead of computational physicists. I was confident because I was the only person in the decade of the 1980s that was at the farthest frontier of supercomputing. Only one lone wolf could be at that farthest frontier, and I was that programmer, period. My confidence against the likes of Albert Einstein was the confidence a 16-year-old boy has when challenged to wrestle against an 8-year-old girl. Who is Philip Emeagwali? I am 4 in 10 parts a mathematician. I am 3 in 10 parts a physicist. I am 3 in 10 parts a supercomputer scientist. Who is Philip Emeagwali? I'm a scientist that is the subject of school reports. I was an astronomer who declined an astronomer position in Washington, D.C. I was an astronaut candidate hopeful who was declined by NASA. I was an engineer that worked on 9 US government dams and their reservoirs and power plants that were along the North Platte River in the state of Wyoming, United States. I was a geologist that pushed the frontiers of extreme scale computations in subsurface flow modeling. Yet, I don't have a deep yearning for engineering or geology or astronomy. I have given up on my 1970s and 80s ambition to fly into outer space. The reason I discovered how to solve that grand challenge problem of supercomputing and solved it alone was that I was trained in the United States for the 16 years onward of March 24, 1974. I experimentally programmed supercomputers and did so continuously and onward of June 20, 1974. With that training, I could solve grand challenge problems in supercomputing that were impossible for a scientist trained for only 8 years who could never touch the most massively parallel supercomputer ever built. I, Philip Emeagwali, was the lone wolf and the only full-time programmer of the most massively parallel supercomputer that was ever built as of 1989. Where was Philip Emeagwali? After 16 years of training, I became a research physicist at the frontier of knowledge of fluid dynamics, and I became a research mathematician at the frontier of knowledge of the partial differential equation of a new calculus, and I became a research algebraist at the frontier of knowledge of the extreme scale system of equations of a new algebra, and I became a research computer scientist at the frontier of knowledge of massively parallel processing, and I became the lone wolf researcher at the terra incognita of the fastest computations. What did Philip Emeagwali discover? After 16 years of training and as many years of supercomputing, I discovered how to massively parallel process and how to compute across a new internet that's de facto a new supercomputer that's a global network of 64 binary thousand commodity processors. For 16 years and in the United States, I conducted research as a lone wolf black supercomputer scientist. Research in supercomputing is conducted at the frontiers of physics and mathematics and computing, and for that reason, it is intensively collaborative. Back in the 1970s and 80s, no white supercomputer scientist had collaborated with a black supercomputer scientist. And white supercomputer scientists that agreed to collaborate with me withdrew their offer after they discovered that I was black. For that reason, I conducted research alone and at the farthest frontier of supercomputing. From those rejections, I learned that when one door closes, another opens. Because I was a lone wolf supercomputer scientist during the 16 years onward of June 20, 1974, I was described as the father of the parallel processing supercomputer that is a global network of commodity processors, and that is a new internet. There is a point of pride in saying I never collaborated with any scientist or scientific team. For that reason, I don't have a co-discoverer or a co-inventor. That co-discoverer would have diluted my contribution, that is the subject of school reports on the development of the massively parallel supercomputer that was a new internet and that was a global network of 64 binary thousand commodity processors. Again, who is Philip Emeagwali? In the early 1990s, I was appointed as a distinguished speaker of the Association for Computing Machinery, or ACM for short. The association's mission was to advance computing as a science and as a profession, and one way the ACM advanced computing was to send distinguished speakers to chapters of the ACM and to universities. The Association for Computing Machinery is the world's oldest computer society. The ACM's Distinguished Speaker Program sponsored, quote, talks with and by technology leaders and innovators, unquote. The ACM sponsored my lectures at its chapters and to American universities. An ACM distinguished speaker serves as a role model to its members and to up-and-coming scientists and engineers. My goal as an ACM distinguished speaker was to teach how I experimentally discovered what makes computers faster and makes supercomputers fastest, and how I experimentally invented how and why to use that new supercomputer knowledge to build a new supercomputer that encircled a globe and encircled it in the manner the internet encircled a globe. I was a research supercomputer scientist that took huge risks. My massively parallel processing supercomputer research called for a polymath rather than for only a mathematician. The supercomputer research is inherently interdisciplinary, and therefore it calls for the full spectrum dominance and the control of both the cerebral and the physical instruments needed to discover much faster computers. My instrument of supercomputer research, whether it's my cerebral partial differential equations of my new calculus or my physical 65,536 processors that outlined my new internet, is what enabled me to intellectually see solutions that are impossible to see with only my biological eyes. The discovery is the discoverer's gift to humanity. The discoverer's hero's journey to the discovery makes her humanity's messenger to the gods. As a research massively parallel processing supercomputer scientist, I focused on attempting to compute answers that were considered impossible to compute, and to do so on the fastest vector processing supercomputers. My quest was for new knowledge, new algebra, new calculus, a new supercomputer, and a new internet. And my intellectual journey was to the frontiers of mathematical, scientific, and technological knowledge. At 10:15 a.m. New York time of the 4th of July of 1989, I reached a previously unknown place that seems to be the end of knowledge. Instead, it was the beginning of ignorance and a place that no man had ever gone before. It was at that uncharted territory of computational physics that I discovered that the most important law in physics, namely the second law of motion, is violated during its most important application, namely discovering and recovering the oil and gas that is flowing 1 mile deep and flowing beneath the surface of the Niger Delta oil fields of Nigeria. It was at that frontier of mathematical knowledge that I discovered errors in the century-old partial differential equations of calculus and physics that were formulated and used in the petroleum reservoir simulation codes that were used by ExxonMobil Corporation and that was endorsed by all the textbooks on porous media flows and endorsed by the entire petroleum industry. I corrected their mathematical errors. What made the news headlines about my discovery of the 4th of July of 1989 was that I discovered a new and improved technology, namely a new massively parallel processing supercomputer that is a new internet, that is a global network of 65,536 commodity off-the-shelf processors And most importantly, I provided concrete experimental evidence that the new massively parallel processing supercomputer is 65,536 times faster than the old sequential processing computer. I experimentally discovered that the impossible to compute is in fact possible to compute. My experimental discovery is summed up as follows. On the 4th of July of 1989, I saw a new supercomputer that was a new internet. And I saw and understood both technologies in a way that was previously unseen. The scientific discoverer discovered a new scientific land that was previously unseen. In my scientific lectures, I focused on my discoveries rather than on my research. To place a higher value on the research than on the discovery is to claim that the search for the truth is more valuable than the possession of the truth that was being searched for. How did I solve the toughest problem in computational physics? The secret is that I had voices from the 16th dimensional hyperspace. Metaphorically speaking, I discovered that the laws of physics and the equations of mathematics that encoded those laws and the algebraic algorithms that discretized those equations and the computer codes that communicated those algebraic equations and that sent and received them across a new internet that is a global network of 64 binary thousand processors contained what felt like a poetry and contained my data and my thoughts that sang their own songs and sang them with the data dancing across my 16 times 2 to the power 16 or 1,048,576 bidirectional email pathways and dancing towards my 2 to the power 16 or 65,536 processors. My data circulated endlessly and circulated towards the everlasting infinity of a new internet that had centers everywhere, circumference nowhere. Back in the 1970s and 80s, my research in the massively parallel processing supercomputer was ridiculed, mocked, and rejected by the vector processing supercomputer community. In the June 14, 1976 issue of the Computer World, the flagship publication of the world of computing, the foremost experts in the field of supercomputing mocked parallel processing supercomputer technology as a quote-unquote waste of time and ridiculed parallel processing as large and clumsy. For me, Philip Emeagwali, my quest for the fastest computation across a new internet that was powered by 2 to the power 16 commodity off-the-shelf processors was de facto the chant of a lone wolf massively parallel processing programmer that was hearing voices from the 16th dimensional hyperspace. In the 1970s and 80s, I wrote voluminously in my private supercomputer laboratory notebooks, and I wrote with the hope that my writings will endure and survive the ravages of the millennia and hopefully become my tangible connection to our posthuman descendants of year million. I kept my handwritten notes private because the things that I saw that were previously unseen by any human being were inner poems that were revealed only to me and that I stole from God's book of knowledge. To you, my friend, the internet is where you send your emails. For me, Philip Emeagwali, my new internet transcends your simple definition of an internet. My new internet is my river of knowledge that has 1,048,576 bidirectional tributaries that fed arithmetical data into 65,536 electronic brains that as an ensemble is metaphorically shaped like the vertices and the edges of the cube in my imaginary 16-dimensional hyperspace. In the first half of the 1980s, I described myself as a research mathematician that was in quest for new mathematical knowledge. My mathematical quest was to discover the fastest floating point arithmetical calculations that had not been described in any textbook on advanced computer arithmetic, a field of study called numerical analysis. I wanted to experimentally discover that fastest computation and experimentally discover it across a new internet that is a global network of 65,536 commodity processors. My mathematical quest was to invent how to solve the largest system of equations that had not been described in any textbook on the subject of extreme scale algebra. I wanted to solve that largest system of equations of a new algebra and solve it across a small copy of the internet. That new internet is a global network of 64 binary thousand commodity processors. These systems of equations of algebra arise from discretizing a system of partial differential equations of a new calculus and discretizing them with explicit finite difference discretization schemes. My mathematical quest was to invent the most accurate partial differential equations that will be more accurate than any partial differential equation in any textbook on the advanced calculus of the flow of oil, water, and natural gas through a porous medium, such as through an oil field. These partial differential equations arise from encoding the laws of physics and from using them in petroleum reservoir simulators that are used to discover and recover otherwise undiscoverable and unrecoverable oil and gas. To become the first person to know equations that are not in any mathematics textbook required that I foremost know equations that are known in arithmetic, algebra, and calculus. Wizardry is to possess the command of materials and possess it from the storyboard to to the blackboard, to the motherboard. For me, Philip Emeagwali, to contribute to mathematical knowledge and to be the cover story of the top mathematics publications required that I know calculus forward and backward and know algebra sideways. That quest for new mathematical knowledge was the reason most of my friends in the research scientific community were mathematicians, not computer scientists or physicists. Every Tuesday morning and at 10 a.m. of the first half of the 1980s, I religiously attended research seminars that were given by research mathematicians that were visiting the Washington, D.C., College Park, Maryland, and Baltimore, Maryland metropolitan areas. Those research mathematicians were at the frontier of mathematical knowledge, were twice my age, and we are visiting from faraway places such as Paris, France, or London, England, or Moscow, Soviet Union. 10 years later, my mathematical maturity had grown, and I was ready for prime time and to share my contributions to mathematics. So it did not come as a surprise to mathematicians that knew me in the 1970s and 80s that my mathematical discovery was the cover story of the May 1990 issue of Science News, the flagship publication of the mathematics community and of the Society for Industrial and Applied Mathematics. That cover story was the reason I was invited to deliver a lecture on my contributions to mathematics and deliver the lecture to the International Congress of Industrial and Applied Mathematics called ICM 91 and deliver the lecture on July 8, 1991 and to the global gathering of mathematicians that takes place once every 4 years. In the lecture I delivered at the International Congress of Industrial and Applied Mathematics, I explained how I discovered a serious mathematical mistake in the advanced calculus textbooks that were consulted by petroleum geologists. The mathematical errors in those calculus textbooks entered into petroleum reservoir simulators that were used to discover and recover otherwise undiscoverable and unrecoverable oil and gas. In computational physics textbooks, the governing system of partial differential equations for multi-phase flow of oil, water, and natural gas flowing across a porous medium could be classified as either parabolic or hyperbolic or elliptic. For a century, the textbooks on the mathematical physics of porous media flows incorrectly derived and misclassified those systems of 9 coupled, nonlinear, and time-dependent partial differential equations of modern calculus. The calculus textbooks incorrectly classified the partial differential equations that governed petroleum reservoir simulation as parabolic instead of as hyperbolic. Mistakes are very common in the equations of mathematical physics. Back in mid-1981 and in a physics research seminar at College Park, Maryland, I was laughed at and dismissed as a crank when I pointed out that the physicist Enrico Fermi had incorrectly stated the equations in his widely reprinted blackboard photo. The representation of that photo of Enrico Fermi was reprinted on both the Italian and the United States postage stamps. Enrico Fermi was nicknamed, quote unquote, the Pope because it was alleged that he never made mathematical mistakes. I had the last laugh when those research physicists discovered that I was right and that Enrico Fermi was wrong. Back in the early 1980s, and in a physics research seminar at College Park, Maryland, I was laughed at and dismissed as a crank when I pointed out that Albert Einstein did not invent the equation E equals mc squared, and that Albert Einstein incorrectly derived the equation E equals mc squared. I had the last laugh when those research physicists discovered that I was right and that Albert Einstein was wrong. My contributions to calculus is this: I correctly derived the partial differential equation of calculus that is used by the petroleum industry, and I correctly classified them as hyperbolic, and I did so when the calculus textbooks incorrectly classified them as parabolic. The partial differential equation is the most advanced expression in calculus and the most important equation in mathematics. As a research mathematical physicist, I discovered that the reason the partial differential equation of petroleum geology was parabolic instead of hyperbolic, as I theorized, was that only three forces, namely pressure, viscous, and gravitational forces, were summed up when summing up the forces used to derive those partial differential equations. As a research physicist that was at the frontier of knowledge of fluid dynamics, I knew that four physical forces govern the motions of water above the surface of the earth, such as in rivers, lakes, and oceans, and govern the motions of air and moisture in the Earth's atmosphere. I also knew that those same four physical forces govern the subterranean motions of fluids below the surface of the earth, such as oil, water, and natural gas, flowing from water injection wells to oil and gas production wells. I discovered that the fourth force, the temporal and the convective inertial forces, were missing in textbooks on porous media flow and that were used by the petroleum industry. After I corrected the mathematical errors, the governing partial differential equations became hyperbolic. I corrected the mathematical errors by accounting for the missing inertial forces. And for the first time in porous media flow modeling, F is equal to MA, or the sum of the forces is equal to the product of mass times acceleration. The introductory textbook on how to solve partial differential equations of calculus uses the classic heat equation of physics as analytical and computational test beds. For that reason, I also used the heat equation as my analytical and computational test beds. The reason I used the heat equation is that it is parabolic. The mathematical structure of the system of coupled nonlinear and time-dependent partial differential equations that governs the multi-phase flows of oil, water, and natural gas flowing through a porous medium is also parabolic. Consider the two-dimensional heat equation and the grand challenge of solving it across a small copy of the internet and solving it in the 1970s and 80s when it was believed to be impossible to parallel process. Imagine that small internet as a global network of 65,536 commodity processors that are identical to each other and that are equal distances afar and apart. Consider the grand challenge of solving that initial boundary value problem that was governed by the heat equation and solving the problem 65,536 times faster than is possible to solve on only one processor that is not a member of an ensemble of processors. Back in the 1970s and 80s, I was warned that parallel processing is a huge waste of everybody's time, and I was warned that it will forever remain impossible to solve the heat equation and solve it across my small internet. I was warned that, according to Amdahl's law of parallel processing, that it will be impossible for me to achieve an 8-fold speedup and achieve that speedup across an ensemble of 8 processors. The heat equation, when restated in prose, instead of in its native calculus, had the partial of temperature with respect to time to be equal to the product of kappa and the sum of the second partial of temperature with respect to x and the second partial of temperature with respect to y. The heat equation, as I described it, has one dependent variable and 3 independent variables. As a large-scale computational mathematician, I devoted a good part of the early 1980s doing theoretical stability analysis of finite difference algebraic approximations of the heat equations, as well as the stability analysis of its cousin of the opposite sex, known as the wave equation. I am an extreme-scale computational mathematician that conducted stability analysis of finite difference approximations of partial differential equations of calculus. I conducted those stability analyses in the early 1980s and in Washington, D.C. I computed my Courant numbers that yielded a priori the stability conditions or the time step restrictions for my petroleum reservoir models, simulations, or general circulation models. As a research computational mathematician, I theoretically analyzed the stability of the error propagation rates of the system of partial difference equations that approximated the system of coupled nonlinear and time-dependent partial differential equations that governs my initial boundary value problems of extreme-scale computational physics. For my stability analysis, I used the Fourier method of decomposition of the initial errors into Fourier series. I also used the matrix method of stability analysis. Like all stability analysis, mine were also limited to simplified linearized versions of the extreme-scaled problems. That is, I simplified my initial boundary value problem to an analogous problem with constant coefficient and with periodic boundary conditions. I theoretically conducted the error propagation analysis for my partial difference equations of algebra and conducted them by Taylor's expansion. After I had established the consistency and the stability of my partial difference equations, I invoked the equivalence theorem to claim the convergence of the solutions of the system of partial difference equations of algebra to the solutions of the companion system of partial differential equations of calculus. I conducted my consistency and stability analysis, both theoretically on the blackboard and experimentally on the motherboard. From my decade-long experience, I knew that the stability criterion for explicit finite difference approximations of the parabolic partial differential equation, such as the heat equation, becomes more stringent as the computational fluid dynamics code changes from 1 to 2 dimensions. It becomes more stringent as the code changes from 2 to 3 dimensions. To avoid such stringent stability conditions, computational mathematicians avoided explicit finite difference approximations that can be massively parallel processed and embraced implicit finite difference approximations that cannot be massively parallel processed. Implicit discretization made sense with the sequential processing supercomputers of the 1940s, 50s, 60s, and 70s. But implicit finite difference discretizations made no sense with the massively parallel processing supercomputers that I was programming in the 1980s. The most popular implicit finite difference approximations were those derived from the alternating direction implicit finite difference methods. Those methods were popular because alternating direction implicit methods yield a set of tridiagonal system of equations, and computational mathematicians love the simplicity of tridiagonal systems of equations as opposed to the messy, dense matrix associated with most systems of equations of algebra. Algebraists loved tridiagonal systems because they can be solved efficiently, as described in linear algebra textbooks. Tridiagonal systems can be solved with small operations count and solved on sequential processing supercomputers. The problem was that tridiagonal system of equations of algebra cannot be massively parallel processed. That is, tridiagonal system of equations cannot be solved at once or solved across an ensemble of 65,536 commodity processors that were identical to each other and that defined and outlined a new internet. Those commodity processors that I visualized as encircling a globe in the 16th dimensional hyperspace defined my small internet. My mathematical discovery that made the news headlines in 1989 and that was reported in the June 20, 1990 issue of the Wall Street Journal was that I experimentally discovered how to solve initial boundary value problems of calculus and how to solve them across a global network of 64 binary thousand computers that define a large internet. That discovery is my contributions to mathematics. I cannot articulate in 60 minutes how I took 16 years to experimentally discover how to massively parallel process and how to do so across 2 to the power 16 commodity processors. If it took me 16 years to understand how to massively parallel process, it may also take you 16 years to understand my discovery of parallel processing. The complete details of my discoveries and inventions are posted as extended lecture series at my website, emeagwali.com. Mathematics is not a science in its own right. The new calculus that I invented, namely the 9th system of partial differential equations, called Emeagwali's equations, is the middle science that mediates between the mind of man and the motion of objects. It's that intermediary position of my new calculus that prompted the debate on whether new mathematics is discovered or invented. I see the 9 Emeagwali's equations as inventions that were abstracted from the discovery of the second law of motion of physics that occurred 330 years ago. That is, my 36 partial derivative terms that I invented were abstracted from the temporal and convective inertial forces that ensures that the sum of the forces is equal to the product of mass and acceleration. That is, the 9 Emeagwali's equations were abstracted from the second law of motion of physics that were in existence for 13.82 billion years, or since the creation of our universe. The physical law that I encoded into my equations existed 13.82 billion years ago. But the mathematical terms that codified those laws could have been known 13.82 billion years ago, but we are not known then. Daalụnụ, afam bụ Chukwura Philip Emeagwali, abụ m onye Ọnịcha. Anyị ga-afụ na emeagwali.com ka o mesịa. I'm Philip Emeagwali at emeagwali.com. Thank you. Thank you. Thank you.
Insightful and brilliant lecture. Insightful and brilliant lecture.